User interface, software, and technology.
The audio you just heard was wirelessly transmitted through our battery-free Mars stickers. Hi, I'm Nivedita Arora, a PhD student at Georgia Institute of Technology, and I will be presenting our work, Mars. Mars is like your everyday sticky note, but it can wirelessly transmit your touch, swipe, or speech without any battery. Mars weaves rich interaction sensing capabilities into everyday surfaces and objects to sustainably blur the boundary between our digital and physical world. Crossing this boundary allows Mars to offer a diverse set of applications and interactions. Leveraging a thin paper microphone connected to Mars, we can enable audio or speech communication. Mars audio tags can be embedded in a conference brochure and used as an extended microphone for central audio control, allowing the audience to ask questions to the presenter.
What are the power requirements of your prototype?
What are the power requirements of your prototype?
They can also be used for extending the hearing range of smart home devices to particular areas or appliances. For example, a Mars tag sticker on the refrigerator could allow a user to communicate with a faraway Alexa and update their shopping list.
Alexa, add eggs to my shopping list.
Alexa, add eggs to my shopping list.
I've added eggs to your shopping list.
Mars tags can also detect multiple discrete touch points powered by two photodiodes and leveraging inductance-based touch sensing. We create game controllers using Mars tags with two buttons to play the classic game of Pong. We can also show communication of unique IDs using capacitive sensing when Mars tags are powered by photodiodes. For example, a waiterless restaurant can equip its menu using unique IDs to distinguish orders. Swipe-based direction control using capacitive sensing is also possible with Mars tags. For example, we can command a light dimmer with our tag to change its brightness. To enable these applications sustainably, Mars needs to be economically, environmentally, and operationally viable. To illustrate, they must have simple circuitry, no batteries, low maintenance cost, and be seamlessly weaved in the environment. Most wireless interactive systems rely on complex circuitry consisting of thousands or millions of active components, which increases both power cost, requiring bulky costly batteries or large power harvesters. We achieve this in just 9 components, 2 active and 7 passive. We demonstrate that Mars tag can be tuned to different resonant frequencies till 1 MHz in less than 1 microwatt of power with low startup voltage of 380 millivolts and current of 1.5 microamperes on an average. Mars can be powered by nanowatt DC power sources like just one or two photodiodes in ambient office light, a single finger touch on a thermoelectric generator, or in the future AC sources like RF with some added power management. In our system characterization, we found that we can reasonably operate the single frequency based Mars stickers till 12 meters and audio based stickers till 9 meters. In the future, we can double the distance with the bistatic placement of the transmitter and receiver. Given 1 MHz bandwidth, we show that 30 single frequency stickers and 8 audio stickers can operate simultaneously for nanowatt power budget. The system setup consists of a transmitter that produces a high carrier wave and a receiver placed at a distance from the multiple Mars tags. Each Mars tag is tuned to a unique frequency, allowing them to communicate on their individual channels. The plane carrier wave that strikes the Mars tag is modulated and backscattered by the antenna impedance, which is changing based on the sensed information. This is received by the RF receiver and demodulated to extract the interaction. The Mars tag can be split into 3 parts: communication, sensing, and power harvesting. The communication system is an ultra-low power LC oscillator called the modified clap oscillator tuned to a unique frequency that modulates the antenna impedance to embed the sensor information. Our LC oscillator uses a zero threshold MOSFET to amplify the oscillations created by the capacitor and the inductor. An isolating capacitor removes any DC bias from the output signal and feeds into a JFET that passively translates the voltage changes from our signal to impedance changes in the antenna. Many types of analog sensors could be easily integrated into the MARS system by modulating the oscillator frequency. The inductive sensors could be placed in conjunction with L1 to modulate the frequency, while the capacitive sensors in conjunction with C1 or C2 to do the same. Finally, the voltage space sensors can be placed by C1 or C2 along with a varactor to translate the voltage changes to capacitive ones. The low startup voltage and current of our oscillator enables simple power harvester setups with no power management. In fact, a single resistor is used to match the harvester power supply to the requirements of the rest of the circuit. MARS takers open the possibility for building sustainable, maintenance-free interfaces embedded on everyday surfaces and objects, which support natural interaction like touch, swipe, and talk input. Thank you for listening. Please come check out MARS interface stickers during the demo sessions, and we are happy to answer any questions as well.